So class, this screencast is for number 7 on page 176, where we have the Benedictine Abbot and the Westminster Abbey, and I don't know about all these abbots and novice, but I do know in the book what we see is some ghosts or something like that. I think these are the abbots and the whatnot. But all we really need to know is that we have a mass on one side and a mass on the other side, and here's up at the top, this is a pulley, so this is really representing that Atwood machine. And so what we got to try to do is construct a free body diagram for both abbot and the novice, and so I'm going to use A and N in order to describe that. And then we're going to try to apply that Newton's second law to express the acceleration in terms of the weights of the abbots and the novice, as well as some fundamental constants. So, as I begin with my novice and my abbot, I have my free body diagram where I have this tension up and the force due to gravity down. The tension up and the force due to gravity down. I tried indicating on here that the tension and the tension are equal because it's the same string. I'm going to use that this force due to gravity is this mass times gravity, and the mass abbot is ma, the mass of the novice is mn. And so with this, we also have to just indicate, well, where we think it's going to accelerate. I'm going to say that the novice is accelerating up, and in turn, then abbot is accelerating down. And so here's our free body diagrams. And so what we're going to try to do now is apply that Newton's second law to find this acceleration. That's what we're going to try to get to. We know the sum of the forces, that's all the stuff added together, equals to ma. The net force is equal to ma. That's what this Newton's second law essentially tells us. And so what we're going to use is the free body diagrams in order to get to the sum of the forces. So this up plus this down equals ma. This up plus this down equals to ma, while knowing that this tension is the same as this tension. So, and we draw in, when we write out our free body diagram, getting to the Newton's second law, sum of the forces, tension up minus that gravity down, that's the weight, equal to ma. It's accelerating up, so I kept it as positive. The abbot, the tension up minus the gravitational force down, equal to negative ma, where I have it negative because it's accelerating down. Now we know tension in both is the same. So that's why I'm going to solve for tension in one of them and then plug it into the other. So I got to find tension in novice and then plug it into abbot. So I find that this tension is equal to the mass of the novice times the acceleration plus the mass of the novice times the gravity. That's the weight. So then I can plug in that mass of the novice times acceleration plus the mass of the novice times gravity. That is that force due to tension minus that mass of the abbot times gravity equal to negative ma, mass of the abbot times acceleration. Now I have for us this sheet where from here we're going to try to solve for this a and this a to get like terms. So I just move the a and the a to the other side, and the G to the other side. And that's how I'm able to solve for my acceleration. Now, I do have this more drawn out, more step-by-step process, because I know some of us might want to see how this acceleration gets to here. So in the sheet part, I'm going to start with this expression right up top. And if I just move this acceleration term to the other side, I add to both sides, and I'm left with what I have here. Then I'm going to take the G parts and move them to the other side. So now I'm just left with the novice times acceleration, the abbot times the acceleration, equal to the abbot times gravity minus the novice times gravity. So what we're left with is this acceleration term, dividing then by that onto both sides, and now we're left with our term that we're seeing here, that the weight of the abbot minus the weight of the novice divided by their total mass. And that will be our acceleration. Then for part C, it tells us, what does it say in part C? So then in part C, it says, assume that they weigh 200 pounds, or assume the abbot weighs 200 pounds and the novice weighs 100 pounds. And we're going to calculate the acceleration for this abbot. So in this part C, we're using that expression we just derived in part B. Now we know that their weight, 890 and 445, if it's 200 pounds and 100 pounds, then we know that their weight is here. Now, I wrote this in terms of their mass. We could get into this in terms of their weight. I just know that their mass here has a 2-to-1 ratio. We're going to divide kilograms, divide by kilograms here. It's the same ratio that we would get if we take pounds, divide by pounds, or newtons divided by newtons. So I know there's a 2-to-1 ratio here. This 200 pounds is 100 pounds. So I know the mass of A, the abbot, is 2 times as big as the mass of the novice. So that's why I changed this just to a 2 minus that 1 divided by 2 plus the 1. So I get 1/3 of the gravitational acceleration. And that's the acceleration I have for that abbot. And we're going to use then in this expression for part D, where we're going to try to find the time it takes for them to hit the floor. They said they were at 2.5 meters up. We know the acceleration of the system. We know the initial velocity as well. So then this expression just becomes this x equal to 1/2 at squared. So we can solve for that time to be 2 times that distance divided by our acceleration. So we get 1.24 or 1.2 seconds. And then for the novice, abbot lets go, so novice has an acceleration due to gravity. So novice is in free fall. So it falls 2.5 meters with the acceleration due to gravity. We could say the initial velocity is 0. It makes this easier. So then we can get the time in the same fashion to get to be about 0.71 seconds. And so this is what we have for this problem.